So since 2004, Armin has been heading the Institute for Formal Models and Verification at the Johannes Kepler University, Linz in Austria. And also since 2006, he has co-founded the startup Next Up Software Incorporated, which in 2012 was acquired by Trenta, which afterwards merged with Synopsys. From 2000 to 2004, he was assistant professor at the Computer Systems Institute in ETH Zurich. I think something many of you know, that prior to that, he was 1 year a postdoc with Edmund Clark at CMU, thinking about, I'm sure, bounded model checking and many other interesting things. So he has been an author of more than 200 papers and really participated in lots of competitions. I'm amazed that you have been winning 96 medals, including 55 gold medals in international competitions, but also receiving many awards. Let me just mention a few of them. TACA's most influential paper in the first 20 years of TACA's in 2014. The CAP Award in 2018, and more recently, ITCAI Gyre 2019 award. Yeah, so I will simply hand over to you, Armin, and not take more of your time.
Well, thank you a lot for the introduction, also for having me here. So first of all, I picked a pretty bold title, Fueling the SAT Revolution. And this is, of course, trademark Moshe Vardi, so I stole his idea of calling this the SAT Revolution. But I want to give you like a personal touch to it. And so I have this personal SAT solving history slide usually at the end of the talk, and we'll come back to this later. But maybe, like, for those of you who think this is completely odd, like now talking about something like a finite and simple as SAT, let me point out, and this is really kind of here behind this avatar thing, and also related to hammers, which I want to explain. So SAT is currently, I would say, almost everywhere in all reasoning, automated reasoning engines. If you're having an Isabelle model, like what we saw in the last talks, and you would try to prove things in Isabelle, you would call usually, actually, the first thing is calling a hammer, which in turn would either call Z3 or Vampire, and which both would kind of internally rely on SAT technology and maybe even call a SAT solver. So what really happened in the last 10 years, which is also still pretty amazing to me, is that kind of SAT is at the core of all these reasoning engines. But I was like, when I like fixed this slide this morning and also thought about the birthday of Quicksort yesterday, that is discussion of the birthday of Quicksort, which is 60 years back. So we here had this red bar here, and 60 years back we have here Quicksort in 1961, and it's surrounded by DP and DPLL, which are kind of the first methods for doing SAT. And also 50 years ago, here in 71, Stephen Cook proved SAT NP complete. And I'll come back to this later. There was a nice seminar at Berkeley, which was exactly about that. But this day yesterday was so inspiring to me that this morning I woke up and thought, okay, can I actually also do sorting with the SAT solver? And of course, I'm showing you now a demo on this, and the main point of this, of course, is actually, I was not sure that it would actually work, so we will see this. So I have the list of organizers and speakers here. So there are 10 organizers, and if you shuffle them, there's this utility which shuffles the organizers, right? Then you can test your Unix sort, like this one, right? And now I've implemented a SAT sort, which does the same, okay? And now that you see that it's actually a SAT solver behind it, I run it with -v, and you see, yeah, so it's doing something. So this column here is the number of variables of the encoding. This is the number of clauses, and they like decrease over time. And because you're shuffling, you get like different actually results. Now, if I go to the speakers, which are slightly more than speakers, then it gets already, of course, remains simple for our sorting algorithm. But for SAT sort, it gets already a little bit, you see, like a pause here, right? And the reason for that is, of course, if you run this with like -v, that like the encoding gets really big. And I want to show you maybe why it's so big. And for that, I have a very small file we want to sort, like this one here. And yeah, so if we shuffle it, and then we call this SAT sort, and maybe this is also interesting for you. I can actually generate the formula which is behind that. And you remember we had 3 lines, ABC or BCA or whatever. And then what are these numbers? Well, these are the bits of these individual characters, right? And because we have 3 characters, we actually need like 24 bits. And this is just the ASCII encoding of these characters. And then there are like some more clauses. So you read this, for instance, here as x25 is false, x1 is true, or x34 is false. And this makes up the encoding. Now what's, I hoped, of course, and which was not clear 3 hours ago, but I managed. If I now take all the participants, which are 90, and I run this into the SAT sort, then actually this produces quite a large formula, as you can see. So this is like 5 million clauses and 200,000 variables, but it's now random. So I hope it's actually finishing. This might, of course, like changes every time I run this. So it was like around 90 seconds, 19 seconds usually. And yeah, it's sorting. And of course, I could explain what the SAT solver is doing here, but this is not the purpose of this talk. So what I really want to show is, I hope it's really finishing. It's making progress. Variables go down. Even with these big formulas, and you do kind of a dumb encoding, a dumb sort of use of SAT solvers, you get actually sorting algorithm. And of course, like the SAT solver doesn't know anything about sorting. So it just has the constraint that there's like an mapping from the input to the output, which is injective, and the output is sorted. Okay, so this was kind of the 2 motivations I have for this talk. Like this, that SAT is kind of really almost everywhere. I tend to assume, also because for all these like more difficult verification problems for software and hardware, there is usually an NP-hard sub problem. Why should you not use sort of the best technology out there for doing this? But the first thing I want to show you also like something. So this is our handbook from 2009. And this was the first input, like from DPLP, the table of contents. And in the meantime, in 2013, Knuth was writing this book here, which is also about satisfiability. Half of it is, of course, exercises. And he visited us and also played the Bruckner organ. And then in 2015, this book appeared. So it's a kind of 5 years ago, like in the middle. And yeah, so you see here these 318 pages. And it was really also amazing is this is subjects in 7.2.2.2, which is 300 pages. You need to manage that. Okay, now SAT is still like kind of making progress. So actually, when I came to SAT 20 years ago at CMU, I thought like we'll see the same fate of SAT as with BDD. So like maybe it will take for maybe 5-6 years, and then we have found all these things you can find with this, but it's not true. So we have now a new handbook coming out this year. So you see it's now 2 volumes and same cover design. And we got these 7 new chapters. And they're really exciting. And so we're making progress. Some chapters were kind of unforeseen 10 years ago. And let's see, maybe before I retire, we will do a 3rd edition. I don't know. Anyhow, so this, you can buy it now. As you can see, it's just available like a couple of weeks ago. Now, to these medals and competitions, there's another thing I prepared, which is part of this talk, and which I used also for some tweets on Twitter. And this is, I made this because some people, even in the SAT community, said, well, the progress stalled, but it's not true. And so this slide is supposed to show that we actually, even in the last 10 years, and this is about 20 years, we saw like tremendous increase in the reasoning power of SAT solvers. I mean, you saw this in this small example. So like you can handle millions of clauses with these solvers. And what you see here on this slide is the performance of the winners of the SAT competition since 2002, right? So these solvers have been winning actually the application track of the SAT competition since 2002. So I ported them to, say, 64-bit and modern compilers, and then we're running them on this on one cluster, on our cluster here in Linz. And on the y-axis, you see the number of solved instances, and these were all the instances from last year's competition, from 2020. So there were 400 instances, and the best solvers can solve 250. And I claim this really shows that these even in the last 10 years, we improved these solvers dramatically. Last year, there was a particular interesting jump because we integrated like a local search. So this on top is my solver KISAT, which you also saw in action in the other demo. But there were two other solvers, Crypto Minisat and the version of MapleSat, who used similar ideas, also very close to my solver. So we kind of also see that like the field is picking up and people implement ideas which work, and it's continuing to work. So I tweeted that, and there was lots of reactions on that. So people wanted to know how many variables do you have, and well, you saw this already in the demo. We really talk about millions of variables. And I have here another tweet on the right-hand side where somebody tried to use the ESBMC, which is a bounded model checker for verification of deep neural networks. So it's maybe related to what we just saw in the last talk. And Bulector is a bit vector solver and internally uses my old Lingeling SAT solver, which won the competition once in 2013. And it hit the internal limit of 2 to the power 27 variables. And so this is quite amazing that people are now using these solvers for bigger and bigger things. Like it's for me clear that maybe as before I retire, I will need to produce a SAT solver which natively supports 64-bit for variable indices. Okay, there's like more to that. So like there was a really nice finding by actually a PhD student from Cambridge who found a new collider in Conbase Live with the help of my SAT solvers and with ideas of our QBank Conquer. So it's quite nice. So the SAT solvers are used for many things, like for mathematical theorems, for verification, of course, for scheduling, for optimization, but also for kind of finding these games and also proving mathematical theorems. Okay, so this brings me to this slide, which of course I could talk about like, I don't know, like hours, but maybe I try to highlight some things which are important for me. I mean, there's lots of other things. We have these two handbooks, right? And so lots of things happened around 2000. So we did this bounded model checking, which kind of replaced PDDs in model checking with SAT solvers. But at the same time, other took this work from the automated reasoning community on decision procedures and combined it with these SAT solvers. Actually, they combined it with CDCL. This is actually a crucial part, which appeared like some in the middle between 1990 and 2000. And this gave then the rise to SMT. And many people now, of course, like use SMT in many different ways. And inside of SMT, of course, is a SAT solver, and the CDCL technology is essential to get this theory combination working. The reason why this all took off is also because we had another like breakthrough at Princeton with Sharad Malik's group, where they figured out technical things, but also new heuristics. This was improved by my two colleagues from Sweden, Minisat. And then we have here some other technology, which is about like inside SAT solvers, but I probably should not talk about it here. This would be more something for a talk closer in the SAT community. there's one thing which people do not realize, like we also have this local search in SAT, which contributed to the big improvement we saw last year. And this is like a highlight here is the PropSat algorithm by Schöning and Balin in 2012, which is very beautiful and simple and works on practical instances. For the first time, I saw that a local search solver is working on this, and this is of course now in these newest solvers. Then I mentioned already Avatar. This is the technology in Vampire, the leading first order theorem prover, which uses the SAT solver to drive the whole resolution process in this solver. So actually, they would almost very similar than SMT solver ask a SAT solver for a new new set of first order literals which should be combined. And then again, if you would use Isabel and would try to prove something with automatically, then you would ask C3 or you would ask Vampire, and then internally really rely on SAT solving.
So I mean, 5 more minutes. Yeah?
Yep. So the big thing here, because I made it bold, is proofs, and this is something which happened in the last 5 years. So I would say before this picture with KISAT and the local search improvements, I would say last 5 years, the big improvement in SAT was having really huge proofs and proving mathematical theorems with certified checkers. The checkers are proven correct in Isabel, in ACL2, they are checkers. And this is even now mandatory in the SAT competition. So you would need to produce proofs with these SAT solvers. And even industry picked this up. So there are companies in France which require SAT solvers, which produce SAT solver proofs for certification. And this almost concludes my talk here. So I wanted to point out there was a really nice workshop at the Simons Institute, and the talk I gave now is like in a 1-hour version, of course, like a little bit outdated and without demo here as video. But actually before that, they had a boot camp, and you can actually watch me for 7 hours in total explaining SAT solvers if you want. And so this, I refer to that if you really want to know about details, how this is working. And so we're really proud about this handbook. So this might also be something you would be interested in. So thank you for your attention.
Thank you very much. I mean, very nice. I'm applauding. I think we all are. Yeah, whoa, that's a lot of gold medals you have there. Maybe we ask some questions. I have tons of questions. So the first time when I really thought, okay, this SAT solver, maybe there is something to gain there, was when I was in Uppsala, and I met, actually not in Uppsala, I was in SIX in Stockholm, and met a guy called Gunnar Stålmark. I didn't see Gunnar Stålmark. I mean, maybe you can keep up the slide there. I mean, I think this can. Yeah. So I didn't see that. For me, that was really amazing. And he really believed that he had proved P equal NP. So with all, do you think P equals NP? I mean, maybe this is the reason behind the success, or is that something you think about once in a while? Or?
Oh, I mean, it's so the demo I showed you with the sorting, you can make the same demo with say a multiplier circuit. It's the same idea. So you just sort of compute something. It's this generate and test, which is also like this old idea in sort of like Prolog implementations. You generate something you want, and then you put a predicate, right? Now, if you do this for a multiplier circuit and you put a number at the output, you can.
Could you show your slide, this big overview?
I try to, but it's kind of, oh, sorry. I did show it, but it was black. Sorry about that.
Yeah, because it was the end of the presentation.
Yeah. Thanks, sorry. Now? Okay.
Yeah, that's good. I think it's.
So there's this zoom window in the way. So what I wanted to say that actually the instances there are even way smaller than the ones we saw through this sorting. And of course they're hard, right? Because otherwise we could factor. But the same thing, of course, applies. The SAT solver doesn't know anything about like arithmetic at all, right? And the same here, the SAT solver doesn't know anything about like sorting or whether these are strings or whatever.
But I was sort of more referring to the Stolmark methods. It doesn't appear on your line.
Ah, okay. The Stolmark method.
But I think many of these Swedish young guys you talk about.
Yes, exactly.
Niklas
So yes, I should mention this. Yeah, in the long version of this talk, I talk about these guys because the Swedish guy, I also have papers with them. And yeah, so this was like in '89, they even patented it. And I should also tell you the story that Stolmark's company, Ed Clark, noticed that, and then it was actually Anna Grumberg. I'm not sure whether she's here. She actually invited, I think Gunnar, but then Arne Borel actually showed up to a CAF conference in Haifa, and
I was there. I remember. He did not
exactly.
He didn't come himself. Yeah.
And this is also, this was kind of the turning point. I think Shankar was also there, so I remember that. And there was really a point where people said, like, maybe there's a life after BDDs. And that's also what Ed Clark figured. And he hired me and another postdoc to just try to do model checking with SAT. So it was really generated by this talk. However, sort of the real breakthrough in this domain is the CDCL, which we were not aware of actually when we wrote the BMC paper. This
maybe another question from me, because I'm pretty sad that BDD is out of the picture. But BDD deals with quantified Boolean formulas. So what is the story there? It seems that it's only recently that you are doing well on QBF.
I mean,
there was even a chapter in this new edition of the book where I sort of saw something quickly with.
Yeah, so there's a second QBF chapter in there, because like QBF improved like MaxSat, by the way. So MaxSat is the same, happened also, like I didn't put it here on the slide, but they're like these core-based proofs for MaxSat have gave extreme performance improvement in the last, like I would also say, like 12 to 13 years. And the same is true for QBF. And also note that when we did this BMC back then, we actually, the first thing I wrote was a QBF solver, which of course did not work. And then we gave up on this and just did this bounded model checking, right? So like giving up on the completeness was the key to avoid QBF, because these QBF solvers don't work. And now the technology improved dramatically, but like for the original motivation, maybe for sort of like model checking, the way how QBF is currently done is probably not the best thing. So maybe for synthesis, but not for the synthesis you're thinking of, but maybe like combinational synthesis, or synthesis of sort of not unbounded but bounded things, right? For that, QBF could become a killer app, but still needs to be seen. I mean, I haven't given up on BDD, so we just have papers on BDDs again, but that's another story, right?
Warren, you have raised your hand.
Yeah, thank you, Armin. I just wondered why QBF was, in 2026 instead of 2025 or 27. I know.
So I didn't know how to do these dots there at the end graphically. So they're like sort of not really like 1 year apart. So this is flexible. So like.
But I'm trying to. What is your comment about SAT and SMT everywhere? What's that mean?
No, I mean, so it's not the case that really in all these reasoning engines we have SAT and SMT. But we do like places like in operation research. There was like roughly 13 years ago, there was a PhD thesis by Achterberg, which clearly showed that you also should have SAT technology in ILP solvers, right? And this is that's what we understand is now in commercial solvers, right? So it also made its way there. And the same happened in CP. So in CP, the best solvers, the best CP solvers are actually using something like lazy clause generation, and are really relying on SAT solvers as well. So and of course there are cases like if you think about Infer at Facebook, I don't think they're using this yet. But like my feeling is like in all these what has been shown, right? So also when I once talked to Tobias Niprov about this, is like whenever you have such an NP hard sub problem, well, maybe you want to use SAT technology to your advantage. And if you don't, then you can gain something by putting SAT technology in it. And that's why for all this automated reasoning and optimization and scheduling, probably there will be some SAT technology in there. everywhere. That's my point.
So it's this optimization essentially is what you're saying. Okay.
What was that?
I said it sounds as if you're just saying that this is by solving this is a good way to pursue optimizations or optimization problems essentially.
So Daniel Swatch-Narbonne, yeah, please.
So I'm curious about what you think about parallel SAT. Do you think there's good hope for like cooperative SAT solvers, or is it more just the portfolio approach?
Well, I've been working on this like on and off also for a long time. So I was teaching GPU programming courses. I'm now doing lockless programming.
What happened? They're gone.
Armin, I think we lost your audio.
We lost a bit, yeah.
Unmute. I think it's somebody wanted to. Okay, so my point was it's extremely difficult, and we made progress for hard combinatorial problems, like for this, like Pythagorean triples Marine was doing, or show number 5 proofs, or Collat's conjecture. We know that this cube and conquer is really the best way to do currently, and then you can really like make use of 800 cores. But still, like sort of, it's not completely automatic. So you need some encoding brain, and also like you need to tweak the heuristics. You need sort of like, it's almost like interactive proving in a certain sense.
We have a question from Martin Nick's brain. Martin?
Hi, Armin. Thanks for the talk. Hey, I'm going to ask a purposefully difficult question. I noticed that you didn't have extended resolution anywhere on your things that are going to happen in the next 5 years.
Actually, you probably know we have been working, so these proofs, these big proofs also means we have been working on new proof systems. And this is really still sort of exciting research going on. And yeah, so, and this also relates to BDD. So our latest papers actually has a BDD style proof system, which is more powerful than causal proof system. Now, but as soon as you allow arbitrary definitions, you get into this problem that you're as powerful as people can think you are, right? So if you allow extended resolution, you can simulate anything what a processor is doing. So if a processor runs Isabelle, right, you can simulate this with extended resolution. In principle, right? Now, to make this effective is, of course, a completely different story. But that's why currently we're not really working on trying to find good definitions, but maybe on more powerful proof systems, like arithmetic ones, like algebraic ones, or pseudo Boolean, or like this BDD-based proof system I was talking about.
Any more questions? I'm sure we have, all of us have plenty, but we also think about a break. So thank you very much, Armin, for a very nice
Thank you for having me.
Presentation here. So I suggest we meet again in half an hour, same place. Yeah, and we will be meeting Ben Finkbeiner, Cesar Tinelli, and Warren Hunt in the second session. So be there a few minutes before. So in 28 minutes, we can move.